I began using ASAP when I joined Breault Research in 2003. I've worked on huge things like space telescopes, little things like micro displays, and I've gotten to work on classic technologies that have been around forever and brand new technologies that we don't even really talk about. And in some cases, we're not even sure the technologies are going to work. But ASAP allows us to explore the feasibility of these new technologies. Now I'd like to talk about some of the common problems that one encounters in display design and show how we can use ASAP to address those issues. The issues I'm going to talk about include generating geometry for LCD backlight design and looking at color mixing using the ASAP CIE colorimetry feature. So we're going to be talking about display technologies and some of the ways that we can build the geometries and simulate them, and some of the analysis we can do of the results after the fact. Let's take a look at a few simple repeated microstructures. The first one is a pyramid type. We'll just run this and we'll create a few little pyramids, and you'll notice that this is a pyramid that doesn't form a point. It's actually more like a hip roof, but the general family can be used to form pyramids as well. And I'll take a look at it in the 3D viewer to really give you a feel for what that looks like. Now in this case, we're only showing a few repeat units, but the same number of ASAP objects is required, even if we choose to make millions of these repeat units. We essentially have an object for the base plane, an object for the roof, and an object for the transverse direction to that roof. So even if we created a million copies, we would still have 3 objects. Another interesting arrayed microstructure that we can look at is lenses, microlenses. In this case, I have a series of toric lenses. Toric meaning that they have a different radius of curvature in one direction than in the other. You can see that these are little microlenses that are sitting on a post, and again, we have a base plane, the lens surface itself, and the edge that it forms to raise it up off the base plane. So 3 objects, even if we create millions of them. Another kind of microstructure is toroids. These are basically little toroids that have elliptical cross sections, and when we look at those in the 3D viewer, they might look like a popular pastry or like the pan used to make a pastry. But these are little microstructures that have particular lensing characteristics that are useful in some kinds of display technologies. And in this case, we only have 2 objects, the base plane and the toroid itself. This structure actually will result in more objects, but not very many more. This structure is a hexagonal pyramid. So it is basically forming an apex in 3 different directions with 60-degree rotations relative to one another. And the result is, just to look at it very closely, a sort of tent-like structure. And this also is a peen structure that could be used in display backlighting or other kinds of display applications. So we're going to be talking about display technologies and some of the ways that we can build the geometries and simulate them, and some of the analysis we can do of the results after the fact. Let's take a look at a few simple repeated microstructures. The first one is a pyramid type. We'll just run this and we'll create a few little pyramids, and you'll notice that this is a pyramid that doesn't form a point. It's actually more like a hip roof, but the general family can be used to form pyramids as well. and I'll take a look at it in the 3D viewer to really give you a feel for what that looks like. Now in this case, we're only showing a few repeat units, but the same number of ASAP objects is required, even if we choose to make millions of these repeat units. We essentially have an object for the base plane, an object for the roof, and an object for the transverse direction to that roof. So even if we created a million copies, we would still have 3 objects. Another interesting arrayed microstructure that we can look at is lenses, microlenses. In this case, I have a series of toric lenses. Toric meaning that they have a different radius of curvature in one direction than in the other. You can see that these are little microlenses that are sitting on a post, and again, we have a base plane, the lens surface itself, and the edge that it forms to raise it up off the base plane. So 3 objects, even if we create millions of them. Another kind of microstructure is toroids. These are basically little toroids that have elliptical cross-sections, and when we look at those in the 3D viewer, they might look like a popular pastry or like the pan used to make a pastry. But these are little microstructures that have particular lensing characteristics that are useful in some kinds of display technologies. And in this case, we only have 2 objects, the base plane and the toroid itself. This structure actually will result in more objects, but not very many more. This structure is a hexagonal pyramid. So it is basically forming an apex in 3 different directions with 60-degree rotations relative to one another. And the result is, just to look at it very closely, a sort of tent-like structure. And this also is a pin structure that could be used in display backlighting or other kinds of display applications. So now I think we'll try creating a repeat unit in SolidWorks, importing that into ASAP, and using that as a repetitive structure for a backlight unit or some other kind of display application. So we've created this shape in SolidWorks. It's created by a series of sketches, and just to give you a full appreciation for the shape, let's take a look at it. This would be a difficult thing to express in terms of a series of mathematical equations, which is the most often used mode of the array command in ASAP. Let's see how we can use this sketch, or this sketched part, to create a repeat unit in ASAP. This is a script that calls that in. I basically have exported the file to an XML format, and I bring it in using a $read command. The name of the file is coney_2.xml. So we're going to actually take a look at it and see what we produce. First, we get a 2D view of it and a 3D view of it. That's just the basic shape without any repeats. And we're actually going to scan that using the ASAP map function. This is the result of the mapping in the display viewer. So we have a depth map of that object. And this is a meshed version of the copied shape. In this case, we've only created 11 copies, a 3x4 array, but this could be replicated in 1000 by 1000 array or larger in an application where that is useful. And each of these is a little mesh view, much like the view that we had in the 3D viewer of the individual one. But each of these is a perfect copy of the original, and all of them comprise one object, and the base plane is another object. We've seen now how to create a number of basic repetitive shapes. Now let's put all this together and look at some real designs for backlight units. Let's look at a light guide. First, we're going to look at a light guide model with just a few rays. We have 1.1 or 11,000 rays. We're going to trace it at full speed just so that you get an idea of the speed with which ASAP traces. This structure has repetitive ellipsoidal dots on the top surface. Those are used to perturb the light pattern inside the guide. We have a reflector on the bottom, and we're illuminating using a CCFL fluorescent light source, a compact fluorescent light source. And we're getting rays bouncing through the unit. They can bounce many, many times before they come to rest, and we have complete control of that in ASAP. I haven't been very careful about confining rays at the corners. That would be a higher order design effort. But this is just a first pass design for a backlight unit. I've averaged the results here, and one thing you'll notice is that this is a terribly grainy output out of the top of the light guide. This wouldn't be obviously usable, but remember, we started out with only 11,000 rays, so we're not really sampling the top surface very well. Let's now take a look at the same problem, but with more rays. So in this case, I've set 1,000,000 rays. I'm going to skip a significant number of the rays, so I will plot only 1 in about 10,000 rays, although I will trace all of them. In this, it actually takes longer to plot the graphics for a ray trace than it does to trace the rays themselves. By cutting down on the number that we plot in the 2D graphics window, we're actually going to be much more efficient at tracing, but we're only going to see a few. And this lets us actually see some of the ray trajectories inside the guide. So if we traced every ray, it would already be completely obliterated. It would be filled with color, and we wouldn't be able to see anything in terms of detail. So this lets us watch the ray trace more or less at our leisure and see the result. And it will give us a better statistical result in the end for the irradiance out the top of the light guide, which, remember, is in the upper area here. That ray trace took about 4 minutes, just a bit over 4 minutes to trace 1,000,000 rays. Of course, the plot ended up being fairly filled with rays. There's limited information in that plot. But of course, we also can look at the 3D view. And just to remind you, this is the light guide. This is the actual reflector housing for the CCFL, the cold cathode fluorescent lamp. This is a top surface detector. And what we're actually going to be looking at is the output on this detector. So we're looking at the irradiance across this plane. Let's take a little look inside just so you get an idea of what's here. We see the orange CCFL lamp, and if we peel this back, we actually see the ray trace as it was going on inside. So that's more or less what we saw in the 2D view. And let's take a look in succession at these at the output irradiance. Now, the first irradiance looks a little bit noisy. Even with 1,000,000 rays, we're a little bit short of great statistics. So the first thing we do is, because this has perfect bilateral symmetry, we fold it. And that actually reduces the noise level somewhat, though that may not be obvious to you. And finally, we do a little bit of averaging. We just average each pixel with its neighbors to smooth things out a bit. The same effect could be achieved by using considerably more rays, but this is a good way to get an idea of what our data contain and what they are trying to tell us. You do see the bilateral symmetry because of the folding, but we see something whose average actually may characterize the behavior of the system to a greater extent. Another thing worth noting here is that we actually see some repeat structure, and that repeat structure is actually reflecting the character of the top surface scattering dots in the display design. So if we lined those up to the output of Radiance, we would actually find that this row structure or column structure that we see here has some relation to those dot structures and their repeat. So now let me show you the result for 4 million rays, just so you know how the statistics improves. This simply opens the result for 4 million rays. Actually, let me bring back the 1 million so that we can compare the two side by side. I don't really care too much about the unaveraged results, but let's take a look at the results after averaging for the two cases. So 4 million rays is on the left, 1 million rays is on the right. So this is 1 million rays, this is 4 million rays. And as you see, by looking at the profile of the data for the 4 million rays, we have reduced the noise level considerably. And we're starting to get a real characterization of the irradiance out the top surface. We see definite artifacts from the row structure of the scattering dots. And to some extent, those artifacts are not artifacts, they're a reality in the design. In successive refinements of the design, we would seek to perturb that. Just as a point of reference, the 1 million ray example took about 4 minutes to run. The 4 million ray example took roughly 4 times as long because it does scale almost linearly, as long as the rays are all loaded into memory. So that was a fairly simple display design. Let's look at a very complex display design. First, we're going to look at a display design which has a sawtooth bottom surface with a reflector underneath. It has grooves in the top that distribute the light across the display, and it has a brightness enhancement film structure on top. First, I'm going to show you just those structures on a limited range so that you can see what we're going to be analyzing. What you're seeing here is the actual spots of the LEDs that are illuminating it on the end face of the light pipe, and now we're actually seeing a 2D graphic of the light pipe itself, or the light guide itself being drawn. And we are seeing the top surface, and now we're seeing the lateral distributing grooves on the top surface being drawn. None of that is obvious at this scale, but we'll zoom in a minute to take a closer look at it. We're actually creating the boundaries of the guide now and filling in the little interstitial areas between the grooves. We have now created the coupling structures on the end that the LEDs couple into, and now we're laying the BEF structure on top of it. And now we'll get to see a 3D view of it, which will make it a little bit easier to see the character of the light guide. So remember, this is a limited extent version of the final display design. I've actually taken only a tenth of the display linear area, so a tenth by a tenth of the total display, so that you can actually see the microstructures, because otherwise they'd be so small that it would be kind of hard to take a look at them. We would have to zoom in a lot. So we have the BEF on top, and you see the characteristic roof structure of the BEF. The ends are actually sealed, and the BEF is formed by molding a top layer onto a substrate that is a contrasting plastic. And so the BEF is not our central concern here, and its structure is fairly simple. So let's hide the BEF and take a look at the actual light guide. What we have here, let's take a look at a corner so that we can really see the structure. Remember, these spots are the spots that show the point of origin or the plane of origin of each of the LEDs that we're using to illuminate the light guide. We have little cylindrical lens structures on the edge that couple the light into the guide. And then, we'll really have to zoom in to see these well, we have little ridges that stand up above the surface, and these little ridges are cylindrical ridges which cause the light to cross-couple. Instead of having the light from each LED just plunge forward along the guide towards the other end, when we impinge on the top surface and we see these little ribs, it causes the light to be diverted to the side. And when we do a ray trace, you'll see some of that action. Finally, on our tour of this, we have a 30-micron sawtooth on the bottom. The specific angles and things don't really matter for the purpose of our discussion, but we have a sawtooth that is used to selectively couple some of the energy down into the bottom reflector while totally internally reflecting the rest of the energy back up into the guide so it can continue to interact with the top surfaces. So that was just for a visual interaction with the geometry. Now let's actually trace rays in the geometry and see what happens. I'm tracing a very small number of rays in this case, but I'm letting us see a lot of them so that we can really see the interaction. I'm also plotting the geometry at lower resolution so that it plots very quickly, and we actually have all of the elements there. In ASAP, there is a definite distinction between visualization and ray tracing. We can represent a surface for the purpose of visualization very simply, or at very high resolution. But when we ray trace, we use the full mathematical description of all the surfaces. Right now, I'm using a full mathematical description of the surface because we need that to get an accurate ray trace. It takes a little while to plot, even at low resolution, because this is the full design with all of the elements. We have created the interstitial space in the top. We've actually, for the purpose of visualization, left out the rib structure. It will be in the ray trace, but we're not looking at it now because we don't really need it to understand the trace visually. We've created the lens structures on the end, and we're about to create the bottom surface, the sawtooth, the reflector, the spacer that actually keeps this from leaking outside the display system, the BEF, and all of those other elements. So this is actually the sawtooth structure on the bottom being plotted. And after that, I'll expect the BEF to plot, and the spacer, and the top surface. And now we're actually tracing. And you see what I was talking about earlier. The grooves on top are causing this cross-coupling. The LEDs are blasting rays into the light guide, and if they continued on that trajectory, it would be a terrible light guide. But the grooves on top, the little rib structures on top, actually help to cross the rays laterally so that the LEDs fill in the gaps between themselves. And the first rays we see are rays that are simply totally internally reflected, but we also have a scattering process on the foil sheet on the bottom. It's a reflector, but it's not a perfect reflector. It's a scattering reflector. So now we're seeing scattering results off the bottom surface, which further causes the rays to be propagated across the light guide, and it also causes some of the rays to be directed back towards the origin, which further helps to fill in the gaps between the LEDs near the launch point. The rays quickly make it hard to see any detailed character for the ray trace, but this gives you an idea of what all the elements in this design are doing for that design. And this is a very simple example, but an example that shows most of the characteristics of the ray trace and of the geometry involved in a simple backlight system. And of course, the rays more or less obliterate the geometry, so I'm going to hide them for a minute and just take another look at this. We have a bezel which actually houses the whole system on the top, and if we remove it, and remove the bezel exit, which is where we measure output, then we see the BEF elements, and I'm just going to hide those, and we're back to the actual light guide. There's also a spacer that keeps the top of the bezel from running into the top of the BEF. So it basically keeps those from scrubbing against each other, but it gives them just the right clearance to all be stacked together. So that is a complete system with the reflector in place, and underneath that, the actual sawtooth structure on the underside of the light guide. And we can actually see that sawtooth structure here. And all of those elements go together to create a working light guide. Having shown you a full display being represented in all of its detail, it would be worthwhile to consider ways that we can make our job easier or more efficient. In the last case, we had bilateral symmetry, and we didn't exploit it in our ray trace. But in some cases, we can speed up the ray trace by eliminating part of the geometry by symmetry. In this case, I'm going to show you that taken to a logical extreme. We're assuming that we have a row of basically one column repeat unit of a display, and that the source and the display itself are all have mirror symmetry about two of its boundaries. You'll see what I mean in just a minute. You can't tell from this side view, but what I am looking at is one column of dots and one source in a display. And if both of those units repeat, then we can use mirror symmetry on the sides of those planes to model the effect of this system without having to model the whole system. In most real systems, this would be an imperfect assumption, but it's a good way to get a very rapid feedback on, for instance, a new dot geometry. As long as we use a lateral repeat unit, we get a result that we can actually consider. So if we look at this in the 3D viewer, you see it's a long, skinny display. And what we have here is these two narrower sides are made mirrors, so that it simulates the effect of having many of these stacked side by side. So we would have this one, and then next to it over here there would be another, and next to it over here there would be another, and so on. And we can stack up the Radiance results to see what this might produce if we build a whole display that way. We see the repeat. This helps us to give thought to how energy is being conducted out of it as we go along the guide, and if we used several randomized cases for these columns, then we could actually make this look so real that one would be hard-pressed to see the difference between that and a full-up display design. This is very effective when you have something like a CCFL that has long cylindrical symmetry, because the source is the same at all points along the guide until you get very near the ends. So this can be a very effective way to look at a display that repeats in pattern. This is an anisotropic look at it. If we make this isotropic, you actually see what the original slice irradiance looks like, but expanding it gives us a better feel for exactly the character of that irradiance function. Let's talk about analysis techniques. So far we know how to build geometry and we know how to trace rays, but in the end we need to actually know how a display performs. An important aspect of display performance is colorimetry. I'm going to talk a bit about the ASAP CIE colorimetry function and things you can do with it. My first example in the colorimetry category is a very simple output of the gamut corners and the gamut edge centers and white point for a display system. And I'm just assuming that the display system that I'm modeling is the display system that I'm using to look at these data for the time being. And what we see is a series of color bars. This is the output, the normal output of the ASAP CIE colorimetry analysis function. We have a three-paned window, and in that three-paned window we have a chromaticity diagram, and exactly which color appearance model and observer model we use is configurable within the tool. We have a display window which shows in physical space what that looks like, and we can see several different colorimetric quantities there. Right now we're looking at an RGB interpretation of those data. And finally, in the bottom, we have, for every measurement pixel in the ASAP analysis window, the colorimetric data for that pixel. So let's just look at this center pixel for a moment. The center pixel is white. If we select a pixel in the display window, we see the corresponding point symbol in the chromaticity diagram highlighted. So white happens to be where the reference illuminant point is pointing, and it's right in the center of the diagram as we expect. If we walk our way through the RGB stack here, the red pixel shows us the red corner. The green pixel here shows us the green corner, and the blue shows us the blue corner. That defines the gamut for the display. Then we have cyan here, which is the midpoint between the green and the blue gamut corners. We have magenta, which is the midpoint between the blue and red gamut corners. And we have this sort of orange-yellow, which is the midpoint between the red and green gamut corners. This was done assuming that the gamma of the monitor, the nonlinearity of the monitor, is 1, which for most displays is not a very good assumption. So let's redo this very quickly, assuming a normal gamma. I'm going to keep everything else the same. I'm going to use the current objects selection as the object for analysis. I'm going to use the current window setting, same number of pixels as we did before, and I'm going to do one other thing. I'm going to display the gamut, because then we'll actually have the color in the chromaticity diagram suppressed for everything that is outside the gamut of the monitor I'm using. So let me hit OK and take a look at the result. A couple of things worth noting. The first thing that I'll note is that that funny orange color is now more yellow, because with an appropriate choice of gamma, that dark yellow or orange looks more appropriate. Using the appropriate gamma for the monitor you're actually looking at is a good idea. And finally, if we look again at these points, we see that they define the gamut corner. Red, green, blue, white is in the middle, and then we have cyan, magenta, and yellow for the midpoints of the gamut envelope for the monitor. So this is a very simple colorimetric illustration of using the RGB intensity function within CIE colorimetry to get a general idea of what the human visual system would gather from looking at this monitor. So we're using a monitor to see how a human would see a monitor, and that's a very interesting application of the CIE colorimetry. While we're here, it's worth noting that other C-Lab coordinates can be displayed. For instance, L star, A star, and B star can be displayed, and their values can actually be probed. And if you really want to know the precise value, then you can actually select a point here and see in the text window below exactly what the values for that are. We can also look at tristimulus values. And in fact, you can configure exactly which quantities you would like to calculate, and ASAP will only calculate the quantities you ask for, within reason, of course. If you have quantities dependent on other quantities, you have to get everything that it takes to make it. But you don't waste time calculating a lot of things that you don't want to see, and you don't display things that you don't need. Now let's do something a little more complex with colorimetry. This is a very simple model of a 3 LED mixing scheme. We have purposely misaligned the LEDs so that they mix reasonably well in the center and not so well around the edges. Let's take a look at that and see how it works. I'm going to run this with a fairly small number of rays first. Basically, I'm running 81 wavelengths per LED and 11,000 rays per wavelength. So that is a modest number of rays for a colorimetric analysis. And I'll show you that result, and then we'll get the result for a great number of rays so that you can see how color noise improves as you use an appropriate number of rays in the analysis. So most of the time spent in this analysis was actually spent creating the sources, because we have 81 wavelengths and a bunch of rays to create at each wavelength. I'll give you a tour of the windows that we raised in a minute, but what this is asking is for me to do the analysis and consider setting the gamma to an appropriate value for the monitor so that the whiteness of the mixing in the center is easily observed. I can choose to show the dialog, the CIE dialog, or not. If I don't, then it'll just run without a dialog and use default values. But I'm going to let the dialog show so that we can actually see how this works. We're going to choose a gamma of 2.4, which is pretty common for commercial monitors. I'll use the current detector, the current window settings. I'm going to change this to fairly low resolution to minimize color noise, and let it go. And we have a CIE analysis window here with the mixing results. Before I talk about that, let's just go through some of the other graphics very quickly. First, this is the actual spectrum of the 3 LEDs. You see that they are well separated in wavelength. We're roughly centered on 425, 525, and 625 nanometers, give or take a bit. And the powers are comparable, but not exactly the same. They're very similar, but not exactly the same. This is a 2D view of the rays coming away from the LEDs. and doesn't really give us a lot of information, but it's just to verify that we did line them up as we intended. So you see the blue source is hanging off the edge a little bit here. The red was plotted last, so it kind of dominates, but you see blue and green hanging off because we've displaced the sources relative to each other. If we look at that in the 3D viewer, we see I've got little red, green, and blue discs to denote exactly where the sources started so that you can tell how the overlap was done. And we've beamed them onto a detector so that we can see exactly what is happening as the sources propagate. So finally we return to the actual CIE analysis window, and we see something that looks rather white in the center, with a little bit of color noise, a little bit of green shading here, and a little bit of red, pinkish shading here, and blue here. We see the mixing in between red and blue into magenta. We see the mixing between blue and green into cyan. And we see the mixing between green and red into yellow. This is with a fairly limited number of rays. Now let me open the result at somewhat higher resolution for a larger number of rays. And in this case, we will have a cleaner definition of white in the center. It's not marked, but it's somewhat improved white in the middle. And more rays always improve these results because, as with any measurement based on statistics, each ray is a statistical trial, and the more rays you have, the better. With monochromatic analysis, we see that as just irradiance noise or intensity noise. With color systems, we actually see color noise on top of all that. So in this case, we have 3 little LED sources with some bandwidth, and we're depicting each of those with a finite number of rays, and more rays improves the situation. Finally, at even higher resolution, I have the 1 million rays, and we really start to get an idea for what a completely smooth result would be. It takes many more rays to do this at a resolution that eliminates the jagged edges, but that's just a matter of time, and in this case, it's an example that runs in just a few minutes. Typically, if you were doing this as a quantitative job for a real display design, you might sample many points on the display, and each of them might take a few hours. But in the overall program of analyzing a display, that's still a fairly small investment in time. So now let's look at the front of screen result of a simple display example. We're actually assuming that we've captured the full chromatic output at the front of screen, and we want to look at the result. The first example I'll show you is an example where we've assumed that we've done everything right, and mixing is pretty good. The assumption I'm making is that we are mixing red, green, and blue LEDs, and this is a small display, so we're only using 2 of each from opposite edges of the display. And in the first case, we're going to produce a result where we don't see the actual artifacts that come from having these discrete LEDs at the edges. This is the result we might get if we had a mixing section outside the actual backlight area that was making certain the RGB LEDs are properly mixed. This is the result if mixing is really good, and I'm going to maximize the display part because that's the actual aspect ratio of the screen, just about that. And this is without gamma properly set, so let's redo the analysis, the CIE analysis calculation briefly, and set the gamma to about 2.4. We're going to use the current object, current window, set its resolution to be the same as the previous one, and take a look at the result. And we should see less color noise here because we're actually using the gamma nonlinearity of the monitor to better express the true range of color and the true saturation of the colors. Okay, so now let's maximize that one and take a look at it. It's a little bit whiter. We see a little bit less intensity or saturation, so we see a better simulation of white. The limited number of rays means that we still don't see perfect white, but if we were very serious about getting a quantitative measurement, we would just use more rays. Now, let's take a look at an imperfect display system. In this case, we've assumed that we don't have good RGB mixing before we come into the display. I won't make you wait for the result. I'll just pull the result up. It takes comparable time to the previous example, but this is an example where we assume that we have red, green, and blue on each of the edges, and we're looking at the mixing and seeing the effect of the poor mixing at the edges. That one was done at a gamma of 1, so let me open one that's done at a gamma of 2.4, more appropriate to the monitor, and let's just take a look. First, I'll just expand this for a minute so you can see that we have the same kind of mixing result in the middle of the display that we had before, but we have imperfect mixing near the edges because we didn't allow a mixing region. So now let's re-expand so that we see the chromaticity diagram and think about what this means a little bit. If we go into, for instance, one of the red regions, then highlight it, we see that those are the points, the redder points are the points that are along that line between the white point and the red gamut corner of the monitor. Those points are showing along that red-white locus. And if we look at the green, we see a similar thing, that the greenest points are way out along the green-white locus, or that line connecting the green gamut corner to the white point of the monitor. And as we go out towards white, we walk along on the chromaticity diagram towards white. And the same can be said of the blue. The points along the blue-white locus are showing up there. And this is at limited resolution, but it's a very real kind of analysis that you might do for a monitor. Typically, this would be used to look in the mixing region if you have a light pipe that is mixing red, green, and blue LEDs. And if you're using side-emitting LEDs, then this may be actually happening right behind your front of display, but you're using the side emission characteristics to do the mixing. And in that case, you might actually have to look at these kinds of results around the arrays of LEDs. So that's a summary of colorimetry. Another important issue that we often encounter is the radiance or radiant intensity functions of monitors as a result of viewing angle. We may want to characterize the viewing angle characteristics of a monitor, and what I have done in this example is to simulate a monitor which has a Lambertian radiant intensity characteristic in the horizontal viewing angle direction, and a super Lambertian. So instead of radiant intensity being a cosine fall-off factor, as in Lambertian, it's actually cosine squared. So we should see a cosine fall-off of the radiance function in the vertical direction. And I'm going to use this to reopen results that I've already created. This example takes a few minutes to run, but I just want to help you out a little bit in seeing it rapidly. Let's look at the Lambertian direction first. Now that looks awful, but the plot scale is not at all appropriate for looking at the full range of the function. So I'm going to use a template that properly scales this. And we see a radiance function plotted by the horizontal viewing angle, and this is from the normal and we're actually starting at about 5 degrees and going out to about 85. And we see that the Lambertian source produces a flat radiance function. So we're Lambertian in the horizontal direction, and we see a flat radiance characteristic in that direction, exactly as we'd expect. In the vertical direction, and again, let me use a plot template to make this a little bit nicer. This is the radiance of a cosine squared intensity dependence in the vertical viewing angle direction. And so in this case, we see cosine fall off in the radiance as we go vertically. And if we carefully look at points along the plot, we find that we have derived a cosine radiance dependence, which is exactly what we would expect. So what happens if you have a new diffuser technology and you have a description of the surface microstructure, but you don't actually have samples yet? What would you do? Well, one thing we can do now is we can use a finite difference time domain code, FDTD solutions by numerical solutions, and couple the far-field scattering characteristics derived from a rigorous electromagnetic model into ASAP as incoherent scatter models. So let's take a look at the numerical desktop, and this is an assembly of randomized ellipsoids on the surface of a dielectric. So these are embedded ellipsoids in the surface of a dielectric. And that shows you the result. We're simulating that geometry, and this geometry would be meshed out and a simulation done, and we would take the near field complex electromagnetic field, project it to the far field, and turn that into one bidirectional scattering distribution function. The randomization means that if we do this many times, the statistics will improve and we'll actually get a function that represents the result if we had an extensive surface, a macroscopic surface with these kinds of characteristics. Now if we take a look at what would result in ASAP, I have a script where I actually load the result in from the numerical simulation. To give you an idea of what that result is, let's just take a look. Numerical actually wrote my raw data functions or raw data models, which will be used to generate a BSDF function for ASAP. And now I'm actually going to do that. I'm going to run an ASAP model where we scatter rays off of that and take a look at the output result. We will create a 2D and a 1D slice of that distribution through the plane of incidence. And those will give us a good idea of how well we have transferred data from the numerical application to ASAP. So now we see a two-dimensional result of the plotting of the scatter field. We see a plot of the model as imported, and what that means is this is exactly what numerical sent us, and this is the actual measured scatter data as the result of tracing rays. So the direct comparison is that this is a 30-degree angle of incidence plot of the actual scatter, and this is a plot of the model. So let's turn off the 0-degree incidence and sort of flick back and forth between the two, and we see the extent to which those two data sets mimic each other, or basically how well does the real reflected scatter signal follow the model that we fed it to create the scatter. This plot is a direct output or a direct result of the numerical far field projection of the near field coherent vector data. The bottom line, I think, is that these compare very closely, and this is a useful result. And in terms of the two-dimensional scatter field, we see something that shows how this works not only in the plane of incidence, but out of the plane of incidence. So this concludes an overview of a potpourri of display modeling, geometry creation, and analysis methods. I hope this has been helpful.